And so it's late on a Saturday afternoon, but welcome to another video in the series on using simulations to understand statistics. And in this video, I'm going to show you how to think about confidence intervals around a sampling mean. But before we start the video, just slide your finger ever so slightly down on your phone, or if you're using a mouse, just move it a little bit onto the subscribe button and just hit that subscribe button for me. That'd be fantastic. So in real life, we calculate a single sample mean that serves as an unbiased point estimate for the population mean. As we can see here, we do a study once and we can only calculate a single mean for some continuous numerical variable. Now the sample mean is an unbiased estimator of the population mean, and that is what we want. We want information about that population mean, but we are uncertain whether our sample mean. So what we would typically do is choose a confidence level, usually 95%, and we create these bounds, intervals around our sample mean, and we express a confidence that the population mean is within those bounds. In reality, what we really mean by that is if we could, at least theoretically, do our study an infinite number of times over and over and over again, that 95% of the confidence intervals that we get will contain the population mean. Now, we only do our study once, and though we set a confidence level of 95%, we can never know if our confidence intervals are one of the 95% that contains the population mean or one of the 5% that do not. Now, we have an equation to calculate confidence intervals around a mean. But this is a series on simulation. So what we're going to do, we're going to use a computer and we're going to simulate the process of calculating confidence intervals. So to begin with, I'm going to generate values for a continuous numerical variable, and I'm going to simulate these values for a population that contains 50,000 subjects. That should be, enough subjects in our population. Now I am going to select these values at random using a chi-squared distribution on 10 degrees of freedom. Now don't worry about that. That is just a distribution that I'm going to use to create these random values. And that's what I do in the line of code right here. Up here, I'm going to execute that. And now I have values for continuous numerical variable for a population that contains 50,000 subjects. Now, since I am the one who created values for the whole population, let's go ahead and calculate a mean for our continuous numerical variable. I can also calculate a standard deviation. So remember, these are population parameters, a population mean and a population standard deviation, and we see the standard deviation there of 4.45491. Now let's create a histogram just to show this distribution. Now remember, this is the whole population, and you can see the dashed blue line there being the population mean, even though the variable itself is not normally distributed in the population. So that was not a requirement, and indeed I chose a chi-squared distribution on 10 degrees of freedom such that I do get a distribution of this variable in the population that is not normally distributed. Now imagine we go out and we select at random 100 people, 100 subjects from this population. And that's what I do right here with the code. And this is completely random. So what we are saying is if we choose these 100 people at random, we don't introduce any bias, is that these 100 subjects must be representative of the whole population of 50,000 individuals. So let's do that. Let's select our sample there of 100 people. Let's look at a smooth histogram just to look at this distribution of values for this variable amongst our 100 subjects. And since this is a series about simulation, let's think about the bootstrap resampling of the mean. Now, bootstrap resampling is also known as resampling with replacement. Now imagine you had a jug in front of you, and inside of that jug was a couple of, let's make it tennis balls. Why not? You can put your hand into the bowl and randomly select a tennis ball and take it out. And what you can do is just take that tennis ball and put it back in the bowl. And you can shake it around, put your hand in and select a tennis ball again, just completely at random, and you can put it back. And that is this idea of random selection with replacement. Every time you've selected a subject, you replace that subject back in the pool for random reselection. And that's exactly what we do here with Bootstrap Resampling. Now think about this. I have 100 subjects at the moment. They were selected at random, so without bias, from the population, and as such they stand as representatives of this whole population. And so what I can do is just consider those 100 subjects as the whole population. And why don't I randomly select 100 subjects with replacement from my 100 subjects? So what does that mean? If I were to do this 100 times so that I can get 100 new values from this population, now I put that population in inverted commas because remember it's just a sample, but we're seeing this as a representation of the whole population. It does mean that some individuals will be chosen more than once. And we might have that some subjects are never chosen. So I'm taking 100 subjects and I'm selecting 100 subjects from those 100 subjects one at a time, but with replacement. Now imagine I do that, and every time I do this selection with replacement so that I get 100 new values, I can calculate a mean. And I can do this over and over and over again, such that I have a distribution of sampling means, but this time it is only done from the 100 subjects that I have for my single study, but they stand as representation of the whole population. So resampling with replacement, and it's very important that my resampling with replacement should end up with the same number of subjects that was in my original study. So I have to select 100 values at random with replacement every time before I calculate a mean. And that's exactly what we simulate here. And I'm going to do this 50,000 times. Now that I've done it 50,000 times, think back at our measures of dispersion. Think about the median. The median was also known as the second quartile or the 50th percentile. 50th percentile, such that that median value would have half of the values less than it and half of the values more than it. But that is the 50th percentile. Let's think about the 2.5% percentile and the 97.5% percentile. Apologies for using percentile and percent, those words so close to each other. But if I were to do that, if I were to think of the 2.5% value, that would mean 2.5% of the values are less than that value and 97.5% are more than. And for percentile 97.5, it means 97.5% of the values are less than and only 2.5% are more than. And so what am I capturing? I'm capturing the middle 95% most common values of all these 50,000 sampling means. And that I'm going to see as my lower bound and my upper bound, and that's exactly what I've done there. So I see a value of 9.89749 and a value of 11.8534. Now think about that. Those are my confidence intervals. Those are values that represent the middle 95% most probable values amongst all these 50,000 sampling means that I do have. Let's have a look at a histogram. And there we see a histogram. Now, of course, by the central limit theorem, even though my original variable was not normally distributed in the population, I do have a sample size of at least 30. In actual fact, I chose 100. And because of that, I can invoke the central limit theorem and look at this distribution of sample means. Of course, it's going to be normally distributed. And what you can see there in the red dashed lines, those are my confidence intervals of these 50,000 sampling means that have been generated by resampling with replacement. I get these bounds that contain the 95% most common values, and those will be my 95% confidence interval. And I've shown you the blue dashed line here. In this case, it so happens that we do capture the population mean within these bounds. Now let's just think about this in a theoretical way. Let's look at the standard normal distribution. There's our standard normal distribution. Now remember, On my horizontal axis, I have z-values, and z-values are units of standard deviation. And remember, for a sampling distribution is scaled by the square root of the sample size, and the standard deviation of a sampling distribution is known as the standard error. So on the horizontal axis, I have z-values, and they represent how many standard errors are we away from zero. And let's select here an alpha value of 0.05, and that means we have 95%. 1 minus 0.5 is 0.95 or 95%, and that's exactly what we see here in the red. And the values of z there are negative 1.96 and positive 1.96. So in this standard normal distribution, what we are telling ourselves is that if we are 1.96 standard errors away from zero, we are capturing the 95% most probable values in this distribution. And because I can take a sample mean and I can convert that to a z-value, all we are saying here theoretically is if I am 1.96 standard errors away from the mean, that will be below the mean and above the mean, that means I will have values around my sample mean representing a 95% confidence level. And that's exactly what we see here in equation number 1. Look at this. It's x bar, the sample mean, plus or minus c. Now c is that confidence coefficient. In this instance, it will be 1.96 times the standard error. That is sigma divided by the square root of n. What are we saying with this equation? We want to be 1.96 standard errors away from x bar, the sample mean. So above and below, minus and then the plus. And you see the values that we have there. We have our sample mean, we have sigma, we have n, our sample size, and we have c. And if we do those calculations, let's do them, we see we get 9.7588 and 10.6212. That is very close to the simulated values that we achieved, not by using any kind of theoretical approach, not by some parameter, not by some parameterized distribution, which carries with it a lot of assumptions. We simply used simulations. We used resampling with replacement. Because we have a computer, we can do that so many times over in a fraction of a second. It is fantastic. And the results are very, very similar to what we find making use of a theoretical distribution.